Will humans ever reach another star? This question is not just a query of engineering or physics. It's a question about our future as a species. It speaks to the deepest parts of our nature. The part that looked up at the moon and wondered. The part that crossed oceans on flimsy wooden ships. The part that is forever driven to see what lies beyond the next hill. The stars have been our companions throughout human history. They have been our calendars, our gods, our maps, and our muses. But could they one day be our destinations? Could we, the inhabitants of a small blue world orbiting a common yellow star, ever embark on the grandest voyage of all? Interstellar travel is the concept of a journey between stars. Not just between planets in our own solar system, like Mars or Jupiter, but a true leap across the cosmic void to the shores of another sun's domain. It represents a monumental step for humanity, a transition from being a species of one world to a species of the cosmos. Think about it. Every person you have ever known, every historical event, every triumph and tragedy has played out on this single, fragile planet. To leave our solar system and reach another star would be to begin an entirely new chapter in the human story, a story written among the galaxies. The dream of interstellar travel is woven into our culture. We see it in our movies, our books, and our most ambitious scientific discussions. It's the ultimate expression of exploration. From the moment our ancestors first looked up at the twinkling lights in the night sky, we have felt their pull. Those points of light are not just random decorations, they are suns, just like our own. Many of them likely have planets of their own, worlds of unimaginable diversity. The possibility of discovering new Earths, new forms of life, or simply new cosmic wonders is a powerful motivator, pushing the boundaries of our imagination and our technology. This journey, however, is not merely a matter of wanting to go. It is a challenge of almost inconceivable scale, a test of our ingenuity, our endurance, and our collective will. It forces us to confront the fundamental laws of the universe, to grapple with the nature of time, space, and life itself. The path to the stars is paved with obstacles that dwarf any we have faced before. But humanity has a long and proud history of doing what was once considered impossible. The quest for interstellar travel is more than a scientific goal. It is a testament to the power of the human spirit to dream, to strive, and to reach for the stars. To truly grasp the challenge of interstellar travel, we must first confront the sheer mind-boggling scale of the universe. Our minds are built for earthly distances, the walk to a neighbor's house, the drive to another city, but the cosmos does not play by these rules. The distances between stars are so vast that our familiar units of miles or kilometers become laughably inadequate. Instead, astronomers use a unit called the light year, which is the distance light travels in 1 year. Light, the fastest thing in the universe, zips along at an incredible 186,000 miles per second. A light year, then, is nearly 6 trillion miles. That's a 6 with 12 zeros after it. Let's take our nearest stellar neighbor, the Alpha Centauri system. It's a triple star system, and the closest of the three, Proxima Centauri, is about 4.24 light years away. That might not sound like much, just a little over 4. But let's put that into perspective. If you were to scale the sun down to the size of a grapefruit, the Earth would be a grain of sand orbiting about 50 feet away. On this same scale, Proxima Centauri, the very next grapefruit, would be over 2,000 miles away. That's the distance from New York City to Denver. The space between them is an almost perfect desolate vacuum. This enormous emptiness is the defining feature of our galaxy. The Milky Way is home to hundreds of billions of stars, but they are spread out across a disk 100,000 light-years in diameter. The space between them is an ocean of nothingness, cold, dark, and unforgiving. It's not just a matter of distance, but of isolation. A journey to Alpha Centauri would take a traveler so far from home that the sun itself would shrink to become just another bright star in the sky, indistinguishable from the countless others. The psychological toll of such a journey, the profound sense of being utterly alone in the cosmos, is a challenge as great as any technological one. Thinking about these distances can feel overwhelming, but it's also a source of deep wonder. It tells us that the universe is far grander and more mysterious than we can easily comprehend. Every star you see in the night sky is an island of light separated by an immense cosmic sea. To cross that sea requires a vessel of extraordinary capability and a crew of extraordinary courage. Understanding this scale is the first and perhaps most important step in appreciating the monumental task of interstellar travel. It transforms the question from "when will we go?" to "how could we possibly ever get there?" Now that we have a sense of the distance, let's consider our speed. Humanity has built some incredibly fast machines. The Parker Solar Probe, designed to study our sun, is one of the fastest objects ever created by humans. At its peak, it can reach speeds of over 430,000 miles per hour. That sounds astonishingly fast, and it is. At that speed, you could travel from New York to Los Angeles in about 20 seconds. But space, as we've established, is a different beast entirely. Even with this incredible velocity, the journey to our nearest stellar neighbor remains impossibly long. Let's do the math. If the Parker Solar Probe were aimed not at our sun, but at Proxima Centauri, how long would the journey take? Despite its record-breaking speed, it would still take approximately 6,600 years to cross the 4.24 light-years of space. 6,600 years. Think about what that means. The Great Pyramids of Giza were built about 4,500 years ago. This journey would take longer than all of recorded human history, from the Bronze Age to today. It's a timescale so vast that it renders the concept of a traditional human mission utterly meaningless. Our current pioneers in interstellar space are the Voyager 1 and 2 probes, launched in 1977. After exploring the outer planets of our solar system, they are now drifting through the interstellar medium, the space between the stars. They are our first emissaries to the galaxy, but they are traveling at a much more leisurely pace, about 38,000 miles per hour. At that speed, Voyager 1 would take over 75,000 years to reach the vicinity of Proxima Centauri. It carries a golden record, a message in a bottle for any civilization that might find it, but it's a bottle that will drift on the cosmic ocean for an unimaginable eternity. The problem is one of energy and propulsion. To accelerate a spacecraft to a significant fraction of the speed of light requires an amount of energy that is staggering to contemplate. Our current rockets work by burning chemical fuel, a process that is fundamentally inefficient for interstellar distances. We are like sailors trying to cross the Pacific Ocean with a set of oars. We can move, yes, but the destination is effectively unreachable. To make interstellar travel a reality, we don't just need a faster ship. We need a completely new way of thinking about motion itself, a new kind of engine that can rewrite the rules of space travel. If our current technology is like a set of oars, what kind of cosmic sailboat or engine do we need to invent? The minds of scientists and dreamers have come up with some truly audacious ideas. These concepts fall into three main categories, each tackling the problem of interstellar travel from a radically different angle. They are the warp drive, which aims to bend the rules of space itself, the generation ship, which accepts the long journey and turns the ship into a mobile world, and the robotic probe, which sends our senses and our intelligence ahead of us, foregoing a human crew entirely. First, let's talk about the generation ship. This is perhaps the most straightforward, if socially complex, solution. The idea is simple. If the journey takes thousands of years, then no single crew will live to see its end. So you build a massive self-sustaining habitat, a miniature Earth in a can. This ship would house a large community of people, with everything needed to survive for centuries: farms, water recycling, a stable ecosystem, and a functioning society. The original crew would live out their lives and have children, and those children would have children, and so on. Many generations would be born, live, and die aboard the ship before it finally reached its destination. Then there are the robotic probes, an idea that is already in motion with projects like Breakthrough Starshot. This concept trades human presence for speed and feasibility. The idea is to send fleets of tiny, wafer-thin probes, each weighing only a few grams. These nanocrafts would have a camera, a processor, and a communication device, and they would be attached to a light sail. An ultra-thin, highly reflective sail. From Earth, a powerful array of lasers would fire a concentrated beam of light at the sail, accelerating the tiny probe to about 20% the speed of light. At that speed, the journey to Alpha Centauri would take a little over 20 years, a manageable time frame for the scientists who launched it. Finally, we have the most speculative and exciting idea of all, the warp drive. Made famous by science fiction like Star Trek, this concept involves not traveling through space, but bending space around the ship. The theoretical Alcubierre drive, for example, proposes a way to expand space-time behind the vessel and contract it in front. This would create a warp bubble that moves the ship from one place to another without the ship itself moving at incredible speeds locally. The ship would essentially ride a wave in the fabric of space-time, potentially allowing for faster-than-light travel without violating Einstein's theory of relativity. It's a concept that requires exotic matter and colossal amounts of energy, but it remains a tantalizing possibility. The line between science fiction and science fact is often blurry, and nowhere is this more true than in the realm of interstellar travel. Ideas that were once the sole property of novelists and screenwriters are now being seriously investigated in laboratories and theoretical physics papers. The warp drive is a perfect example. In the 1990s, physicist Miguel Alcubierre, inspired by Star Trek, developed a mathematical model showing how such a drive could work within the framework of general relativity. His equations were sound, but they came with a catch. They required a form of exotic matter with negative mass energy density, something we have never observed and do not know how to create. Despite this hurdle, scientists at NASA's Eagleworks laboratories and elsewhere continue to explore the concept. They are investigating whether the energy requirements can be reduced to more plausible levels and searching for loopholes in physics that might permit such a phenomenon. A fun fact for science fans: the Alcubierre drive doesn't violate the cosmic speed limit, the speed of light, because the ship inside the bubble is locally at rest. It's the bubble of space-time itself that is moving. It's like standing on a moving walkway at an airport. You aren't running, but your location is changing rapidly relative to the terminal. The Generation ship too has graduated from fiction to serious study. Projects like Biosphere 2 in Arizona were attempts to create closed ecological systems, essentially practice runs for the kind of life support a Generation ship would need. These experiments taught us valuable lessons about the immense difficulty of maintaining a stable, breathable atmosphere and a balanced ecosystem. The challenges are not just technological, but also sociological. How do you govern a society isolated for centuries? How do you maintain a sense of purpose across dozens of generations who will never know their starting point or their destination? Meanwhile, the concept of robotic probes is already taking its first steps. The Breakthrough Starshot initiative, announced by Yuri Milner and the late Stephen Hawking, is a real research and engineering project aiming to develop the technology for laser-propelled nanocrafts. They are tackling immense challenges, such as designing a sail that can withstand the intense energy of the laser beam, and figuring out how a tiny probe can send a signal back to Earth across trillions of miles. These ideas show us that what we dream up in our stories can become the blueprints for our future, pushing our science and engineering to new heights. The journey to the stars is, without question, the most ambitious project humanity could ever undertake. The challenges are monumental, spanning nearly every field of human endeavor. Technologically, we need propulsion systems that are orders of magnitude more powerful and efficient than anything we have today. We need to figure out how to shield a spacecraft and its crew from decades or centuries of exposure to cosmic radiation, a constant rain of high-energy particles that can damage electronics and living tissue. We need to create perfectly closed-loop life support systems that can recycle every drop of water, every breath of air, and every nutrient for generations. Beyond the hardware, the human and biological challenges are just as daunting. How does the human body adapt to zero or low gravity over centuries? What are the psychological effects of living in a confined space, forever separated from Earth, with only the blackness of space outside the window? For a Generation ship, how do we ensure genetic diversity and social stability in a small, isolated population? These are questions of biology, sociology, and psychology that we are only just beginning to ask, let alone answer. The resources required, the energy, the materials, the financial investment, would demand a global collaboration unlike any in human history. And yet, despite these colossal obstacles, there is hope. The dream of interstellar travel is a powerful one because it taps into the very essence of what makes us human. We are explorers, we are problem solvers. The same curiosity that led us out of Africa and across the globe is now turning its gaze to the stars. Each scientific breakthrough, from understanding the fabric of space-time to developing more efficient energy sources, brings us a tiny step closer. The quest itself drives innovation that can have profound benefits for life here on Earth, from new medical technologies to sustainable energy solutions. So, will humans ever reach another star? Perhaps not in our lifetimes or even in the next several centuries. But the journey has already begun. It began with our ancient ancestors who first mapped the constellations. It continued with Galileo, who turned his telescope to the heavens, and with the Apollo astronauts who left the first footprints on another world. Today, it continues in our laboratories, our observatories, and in the dreams of the next generation of scientists and explorers. The stars are calling, and while the voyage is long and the